Okay, so we're going to embark on our next unit in this class, and that is talking about frequency response. And we're going to learn this semester how to sketch the frequency response of our processes. One of the design methods that we will discuss this semester is talking about modifying the frequency response by using control systems. And so this is a verse from an old song that I knew when I was growing up. You probably don't know it. But the song goes something like, Daddy sings bass, Mama sings tenor. Now, that's a little bit weird because women generally don't sing tenor. But I think most of us who have a little bit of music understanding or who have been around choirs understand these words, right? What does that say about these people's voices? How would you describe that?
Really low.
Okay, this individual sings lower notes. This individual sings higher notes. That's a way of describing the characteristics of these individuals through their frequency response. Okay, we've talked about time response in the past. We've talked about step responses. Now we're looking at frequency response as a way of describing the characteristics of an individual. Okay? So we're going to look at frequency response this semester in several different ways. Our topic today is we're going to basically take a look at what is known as the Bode diagram. Okay? This is a Bode diagram, and we are going to sketch them on charts that look like this. So you've been handed out a piece of paper where the grid lines are not uniform. You notice the grid lines are not uniform this way. And we're going to talk a little bit about these grid lines today, talk a little bit about the Bode diagram. And then what we want to do this semester is we want to learn how to quickly sketch. We want to sketch them. We want to learn how to also use the computer to generate them. Okay, there's an easy command to do this in MATLAB. There are some characteristics that we need to be able to read. So when I say read, I'm basically saying I need to be able to look at the characteristics that we sketch and basically analyze the characteristics. And we'll talk about a few of them today. Okay. So these are the things initially what we're going to do. Eventually, we're going to use these diagrams. These diagrams tell us some characteristics of the process. And we're going to use these diagrams, and we can tell whether or not our process, if we put it in feedback, whether it be stable and what is the nature of the overall system using frequency response. Okay? So our focus today is the Bode diagram. It's frequency response. And so I'd like to turn your attention to, let's first take a look at what we call semi-log paper. So the Bode diagram is basically two charts. Okay, they're basically two plots. One of them is what we're going to do is one of the plots is going to be the magnitude of the system. Sometimes people call it the gain of the system. And it's plotted using a unit called dB, which is an abbreviation for decibels. Okay? And on the other axis, we're going to plot frequency. That's why it's called a frequency response. It is a function of frequency, magnitude versus frequency in dB. And this is on a log scale. Okay. The other plot is going to be the phase of the system. Some people call this the delay. You know, when something goes into a system, when we excite a system, it takes a bit of time for the system to respond. Okay, so that's why we say it's a delay. And we measure that delay. We can describe that delay in degrees Okay, and then this is also as a function of frequency on the same log scale. Okay, so these are the two Bode diagrams. Now, let me talk a little bit about this piece of paper. And so I put basically two pieces of this chart on here. And we kind of need to figure out what's going on here, which way to orient this thing. Okay? And so let me come back and talk a little bit about this frequency axis and why it's, first of all, talked about on a log scale. Okay? We use a log scale to cover a wide frequency range, a wide range of frequencies. Okay? Anybody here or buy a piece of audio equipment lately? Maybe put in a stereo in your car because you're driving an old car and you want to put a new one, right? So you look at the specifications, you go to the dealership that's selling the radio and you say, what's the frequency response? And they say something like 20 hertz to 20 kilohertz, okay? And so imagine we're trying to say we want to cover 20 hertz to 20 kilohertz, 20 hertz to 20 kilohertz, okay? So let's start plotting this on a linear scale. We would say here's 0, here's 10, here's 20, that's good. Here's 30, here's 40, here's 50, here's 60, and now we start seeing problems. Okay, this is hertz. We're already off the page, and I'm not even to 100. So imagine where I'm going to be at 1,000. I'm going to be way out there. All right. So what we do is rather than plotting on a linear scale, we use a logarithmic scale. And so let's take a look at the log function. Just as a brief review, the log function let's call this x, and this is going to be the log of x. Okay. Log function looks something like this. All right, the log of 1 is 0. And what happens is that large values get squished down. It gets compressed. Okay? So large values are compressed. Okay? So for example, if I take log of 100, this is base 10, the result is 2. So 100 gets compressed down to 2. Log base 10 of 1,000 is equal to 3. Okay? So I get this great compression. On the other hand, down here the slope is large, and so small values are expanded. Okay? So large values are compressed, small values are expanded. And so when we take a look at this piece of paper, we've got to figure out which way are we supposed to orient things. So we want to orient things this way because here the scale is linear. Okay? And we're going to plot frequency on this horizontal axis. And so we want to plot it in such a way that it looks like the high frequencies are compressed and the low frequencies are expanded. Okay? So the way I've got it oriented right now is upside down. So this is the orientation. This is the proper orientation. So you take a look at the frequency scales here. See how the large numbers are kind of squeezed in this way. If you sit farther back, you're going to see here, it looks like there's a kind of a repeating pattern here. Okay? And so this particular type of log paper that you see here, you see there's kind of a band of frequencies here, followed by another second cycle of frequencies, followed by a third band, followed by a fourth band of frequencies. And so this particular log paper, this is called 4-cycle. Okay? And you see that the compression is only on one axis. the vertical axis is not compressed. So this is called 4-cycle semi-log paper. Okay. MATLAB has a command to plot things in a semi-logarithmic fashion. You could put the compression on this axis, that's called semi-log x, or you could plot it this way. Things would be on a vertical axis, that would be semi-log y, but we plot things horizontally this way. Okay, let me show you how we typically label these things. We have to identify these things that we call major divisions, okay? And so the major divisions are going to be here. So for example, one way I could label this is I'm going to call this 0 right here, but this is not the normal 0. This is 10 to the 0. Okay? So 10 to the 0 is 1. Okay, so let's zoom in a little bit and take a look at this. This is 1. This is 2. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, count that real carefully. Kind of zoom in for it the first time. This is 10 to the 0. That's 1, 2, 3. Count it carefully. 4, 5, 6, 7, 8, 9, 10. This is 10. This is 1. 10 raised to the 1. So this is a major division, and here is another major division. And let's zoom back out so we can see our major divisions starting to appear before our eyes. This is a major division. 0, 1. This is going to be 2. 10 to the 2. Here's the major tick mark. This is going to be 3. 10 to the 3. In this case is going to be 4. 10 to the 4. So this is one way I could set it up, my frequency axis. And so I'm going to label this axis as frequency. Now, in school, the usual unit of frequency is radians per unit time. Radians per second, as an example, radians per second. Okay? If you ask the computer, if you ask MATLAB to generate a Bode plot, it's going to default to this unit, radians per second. Now, in practice, if you're using a machine, like you go to Dr. Riggs' lab and he's got a spectrum analyzer, we're not going to use radians, we're going to use something like hertz, cycles per second. That's another unit. And we know that there's a relationship between these two. There's a 2 pi in there that's related between the two. One of these is called omega, and the other one is f. Okay, so this is the frequency axis. Okay. Let's take a look a little bit in more detail and see how we should be looking at these frequency axes here. This is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, right? 11, 12, 13, 14. No, that doesn't work. Okay? This is 10, this is 100. So this is 20. This is 30. This is 40. Okay? Where's 11? 11 is somewhere in here. Okay, so there's a distortion of the frequency axis. We need the distortion of the frequency axis in order to get large frequencies onto the picture. So that being that this is 10, this is 100, this is right here, this is 200. And this is 2,000. Okay. You need to understand how to orient the paper. Some commercial papers that are printed, you know, this is kind of like you see it here. This is kind of a solid line. Okay, these major divisions are solid lines. And we want to put basically the exponent right here. I could have also maybe put 0 somewhere else. I could have put 0 right here. As an alternative, I could put 0 right here. This is 10 to the 0. And this would be 10 to the 1. And this would be 10 to the 2. This is another way. This then should be 10 to the minus 1. Okay, at this major division. This would be 10 to the minus 2. In other words, this would be 0.01, 0.1, and so forth. Okay, where is omega equal to 0? Where is omega equal to 0? If this is omega, where is omega equal to 0 on this scale? It's way out there. Okay, it's way out there. So we don't have 0 on the scale. Okay, omega equal to 0 is not on the scale on a Bode diagram. We'll have to extrapolate. We'll have to say, well, this is getting small, so it's somewhere out here. All right, so one of the diagrams that we're going to plot on a Bode diagram, and we're going to learn this one first, is what we call the magnitude plot or the gain plot. So we would label this axis here as magnitude or gain. And the unit is dB. Okay. So this is how we label that one. So this is magnitude versus frequency, y versus x. All right. Now there's a couple definitions of dB. All right. So one of the definitions is to take the log base 10 of our gain. We'll take the log base 10 of our gain. And then multiply by 20. Okay, this is the definition. 20 log gain. Okay? So as an example, if I have a gain of 10, the log of 10 is 1. The log of 10 is 1, and then that's equal to 20 dB. Okay. Now, if you're dealing with electromagnetics, we have a different gain. Okay. How much power we have. So we say 10 log times the power. Because in electromagnetics, let's say we're working on a microwave oven. It's an 1,000 watt oven. Watt is power. Okay? You're working with antennas. How much power are you sending out? And we may remember that a lot of times when we're dealing with our systems, say we draw a block diagram, say here's our system G of S, and we're looking at the input-output signals, a lot of times these are like voltages or current. We use an electronic circuit to measure some characteristic, and it gives us a voltage, maybe a voltage proportional to speed or a current proportional to speed. Does anybody remember the relationship between voltage and power? V squared, right? And so if power is squared, then this would be like voltage squared, and then you may remember the log characteristic. The square comes out, and the 2 comes out, and then this becomes a 20. And so these two are equivalent. Now, we use this particular definition in this class. Okay? So let's zoom out a little bit. This is the way we label our frequency axes and our vertical axes. This is magnitude versus frequency, logarithmic scale to compress this, and then this is on dB, in dB, so we've defined dB now. All right. The other scale or the other diagram is also on the same axes, and so we're going to plot frequency down here, and in this class we'll default to the units radians per second, radians. Find your major tick marks, okay, and put the exponents here. Okay, you cannot arbitrarily say, well, I'm going to put 10 to the 0 right here. You have to put the exponent right here. Anything in between here is a fractional exponent. Okay, so if you want to label, you could call this one 1, 10, 100, 0.1, 0.01. Okay? The understanding is that this is 10 to the 2, 10 to the 1, 10 to the 0, 10 to the minus 1, 10 to the minus 2. Okay? These exponents are what go on the major divisions right here on these lines. Let me pause there for a moment and ask if there are any questions about the frequency axis or the vertical axis, dB. Okay, on this axis, on the phase plot right here, what we do is we typically call this phase. And it's labeled in degrees. So somewhere, maybe we'll just choose this, we'll call this 0 degrees right there. And maybe we'll call this 90 degrees, and this is negative 90 degrees. You choose your scale. Okay? We'll learn in another meeting, we're going to start looking at sketching these out quickly, and then I'll give you some ideas, some suggestions for what these are going to be, how they're going to be scaled. The computer is always going to scale something so that it kind of fits on the screen nicely. So what you get on the screen by computer is not necessarily what you're going to do by hand. By hand, there's some rules of thumb to quickly sketch things, and so we're going to choose some scales here that are easy to work with by hand. Okay, so let's zoom out a little bit and just kind of remind ourselves what's a Bode diagram? The Bode diagram actually is two plots, magnitude versus frequency and phase versus frequency. Okay, so here they are, magnitude versus frequency and phase versus frequency. Magnitude versus frequency, phase versus frequency. And what we're going to do is we're going to basically learn to sketch things in this class. And so one of the things that we're going to see is we're going to put some curves on here. We're actually going to draw straight line approximations here, and then we will fill things in. So maybe there's going to be, for example, maybe something that looks like this. And then here maybe something that looks like this. Okay, so these will be straight line approximations. Okay, these are called asymptotic approximations. Asymptotic means the lines are reasonably accurate. Okay? It's going to turn out that the actual curves are going to be pretty accurate far away from the corners, but near the corners they will do something like this. Okay? Something like this. So the actual curve might look something like this, but we're going to, in this class, learn to sketch these asymptotic lines. Okay? Here in the magnitude plot, away from the corners, these lines are pretty accurate. That's why they're asymptotic. They're called asymptotic. But near the corners, there's going to be some error, and so the actual curve is going to look something like this. The actual curve is what the computer calculates for us, and we're going to learn to kind of sketch these straight line approximations rapidly. Okay? Now, why do we do that? Again, in this day and age, we do real work by computer. The purpose of learning the asymptotic lines is so I have some material to put on an exam. Gosh, I need to retire. No, the reason we do that is because when we plot something, it'd be nice to have in the back of our mind a rough idea of what I think the response is going to look like. And then when the plot comes out and it doesn't look like what I think it looks like, then I need to start thinking, ooh, maybe this problem is more difficult than I thought. And I need to go back to the customer and say, you know, we need another week to analyze this. That's going to cost you. Time is money. Or the other alternative is maybe I entered the model incorrectly in the computer, and I need to recheck before I go further. So the purpose of learning the straight line approximation is so that we have a sanity check when we do real work on the computer. Okay, let me talk a little bit about a characteristic on the magnitude plot. We're going to take a look on the magnitude plot. On magnitude versus frequency, plot, we're going to sketch a hypothetical plot right now. You want to call this omega, okay, radians per second, or call it frequency. On a machine, this would be F, frequency, in hertz. And so we're going to get a response that looks, maybe that looks something like this. Okay. Now this plot over here on this axis, this is supposed to be the gain. I'm going to use this notation to say that's gain. The absolute value is the magnitude. Okay, and the units are in dB. So this means magnitude. In dB. One of the terms that I want to describe today is this idea of bandwidth. Okay, so I want to talk about what is bandwidth. When we first came in, I said, Daddy sings bass, Mama sings tenor. Okay, the implication is that Dad's voice is at low frequency. Okay, he is unable. This is Dad down here. He's unable to sing these high notes, and so there's a bandwidth. There's a limit to how high he can sing. Okay, there are a couple definitions of bandwidth. If you take a look at this plot, on this plot we can say that there is a maximum gain. Okay, so this is a maximum gain. Maximum gain is somewhere here. We don't know. It's got some number. Okay. As frequency increases in most systems, as the frequency increases, the response starts decreasing. Just like a man's voice, he has a difficult time singing at high frequency. A woman's bandwidth is a little higher, but she also has an upper limit. Okay, and so we typically see in real physical systems that the frequency response, the gain, the magnitude decreases. Now, at some point, it has come down to, let's say, right about here. And if I take a look at the scale, this is going to be minus 3 dB below maximum, whatever the maximum is. Okay? If we're dealing with a 741 op-amp, this maximum gain is on the order of about 10 to the 5 or 10 to the 6. That's the gain. Okay? So if you take 10 to the 5, what's the log of 10 to the 5? 5 multiplied by 20, it's 100. It's 100 dB. Okay, the 741 op-amp has very high gain at low frequencies, but then its frequency response starts dropping off very soon. Okay, so what we do is we would look for where the gain has dropped down from 100 dB down to 97. Okay, so it's 3 dB below the maximum. Now, if you do a little bit of study, you say, why is it minus 3 dB? If you take minus 3 dB and take a look at that, this converts, minus 3 dB, but converts to square root 2 over 2, or 0.7071. Okay. What's magical about square root 2 over 2, or 0.707? If you square it, what do we get? A half. Right? So if this was a voltage and you square it, then you're down, the power is a half. And so minus 3 dB is also called the half power bandwidth. Okay, half power bandwidth. So if you're looking at a plot, and you want to find the half power bandwidth, you find out what the maximum gain is, and you see where it drops down 3 dB. 3 dB means the voltage has decreased by a factor of roughly 70%, but the gain is down to half. So I'm only putting out half as much power as I was at the peak, and so we call this value we read it off down here. We read it off right here. This is the half power bandwidth. Okay. Now there's another bandwidth value that is a lot of times used because sometimes it's not possible to. There may be it's not possible on our diagram to see what the maximum gain is. So for example, there's one plot that we're going to look at another day where the frequency response looks like this. Okay, it's just a slope, just a line like this. Well, what is the maximum gain? If I keep on going this way, the maximum gain keeps on going up. And so the maximum gain is infinite. So 3 dB below infinity, or 70% of infinity, is still infinity. So that's not a very useful idea of bandwidth. The other idea of bandwidth is says, well, if the gain is infinite and I cannot find 70% of infinity, let's look for another way. What I could do is I could look and see where the graph gets small, where the gain is small. Okay, so what's the definition of small? We've got to choose a number. What's our favorite engineering number? A gain less than 1. Okay, we'll choose a less gain than 1. So the other thing we could do is we could say, let's take a look not at 3 dB below the maximum, but let's see where we cross here, say 0 dB. 0 dB means unit gain, unity gain. Okay. Let's take the log base 10 of 1 and then multiply by 20. Log of 1 is 0. 20 times 0 is 0. So that's unity gain. So we look at where this thing crosses 0 dB, and we call that the bandwidth. So this is called the unity gain bandwidth. Unity gain bandwidth. Okay. Can't write. Okay. Have you seen the 741 op amp in electronics? Do you still talk about it a little bit? If you're in 3700, 741 op amp has a gain characteristic as a function of frequency. Now this is hertz. At low frequency, this is about on the order of 10 to the 5th. And so 10 to the 5th is like 100 dB. And then it immediately starts rolling off. And it comes down like this. And where it hits 0 dB out here, here's 0 dB. Where it hits 0 dB right here, this is on the order of 1 megahertz, roughly. 1 megahertz. This is where the gain has come down to 1. Here the gain was real large, but as frequency increases, the gain starts decreasing. Along this line, the product of gain and frequency is constant. Here's gain. If you take that gain and multiply times this frequency, you're going to get a number. You take, at this frequency, you get a different gain. The gain is decreased, but the frequency is increased. Here the gain is real large, but the frequency is small. All along here, the product of gain times bandwidth equals a constant. Okay. Here, the gain is 1. The frequency is 1 megahertz. So the gain bandwidth product for this is 1 megahertz. Okay. So in the data sheet, they're going to call it like this, gain bandwidth. In this class, I call it the unity gain bandwidth. Okay. Unity gain bandwidth for 741 op amp is roughly 1.5 megahertz. Okay. At a megahertz, the gain has decreased to 1. 1 times a million is a gain bandwidth product of 10 to the 6th. Okay. So this is something that you probably hear, the gain bandwidth product, you hear this from ELEC 3700. Here we talk about unity gain bandwidth. This is in this course, okay, that we're talking about the same thing. 3 dB bandwidth is way over here. Right here. Minus 3 dB bandwidth. Okay? We usually don't say minus because we get lazy. We just call it 3 dB. The implication is it's 3 dB down from the maximum. So there's two bandwidth figures that are often spoken of. 3 dB bandwidth, which is half power, unity gain, which is another bandwidth. Okay? Now, what we're going to do is, in this class, we're going to be mostly working with plots. So we're going to learn to sketch these plots and then kind of read them off the plots. So that's the skill that we'll do. But just for today, let's try to do a little bit of calculations. Okay, let's try one. Let's suppose that our model, let's do a bandwidth example. Let's do a couple of them. I think we've got enough time. Let's suppose our model is 5 over s plus 3. Okay, 5 over s plus 3. Our first order model, 5 over s plus 3. We're looking at the frequency response. So frequency response means S is equal to j omega. And now this is the independent variable. This is frequency. Okay? So we're looking at the frequency response function, which is g over omega. It's 5 over 3 plus j omega. Okay, so wherever I see s, I just say s is equal to j omega. So that's my frequency response. Now, what we're interested in doing is looking at the magnitude. It's the magnitude of g of omega. So this is a complex number. So the magnitude is taking the magnitude of the top and then finding the magnitude of the bottom. This is a complex number, so we'll have to do something like 3 squared plus omega squared square root. So let's find the bandwidth now. Let's first find the 3 dB bandwidth. Okay, let's find we got the magnitude of g is equal to 5 over 3 squared plus omega squared square root. Okay. The maximum gain is, well, let's take a look at this function. When is it largest? This is the independent variable. When is this overall function the biggest? When omega is equal to 0. So for this particular example, the maximum gain is at omega equal to 0. When omega is equal to 0, I get a gain of 5 over 3. And if I wanted to convert it to dB, I would plug 5 over 3 in, which is 1 2/3. Hit the log button and then multiply by 20. Okay? So 3 dB down, half power is when gain is equal to 5 over 3 times square root 2 over 2. This is my 0.7071. Okay. So let's set this up. So we'll take a look. Here's the gain. The gain is 5 over square root 3 squared plus omega squared equal to 5 over 3. I want to be 3 dB down. 3 dB down means I'm down to 70%. Square root 2 over 2. And I'll solve for omega. Okay? This is algebra for us now. Let's see, the 5 cancels out. Let's square both sides. 1 over 3 squared plus omega squared. Let me square this side. I get 2 over what goes in the denominator? 36? This is 1 over 18. Okay. 3 squared plus omega squared is equal to 18. Omega squared is equal to 9. Omega equal to 3. Okay, so this would be the 3 dB bandwidth. 3 radians per second. 3 radians per second. So that's an example of how we would calculate the 3 dB bandwidth. Okay, the other bandwidth definition was unity gain bandwidth. Zero dB bandwidth. Let's calculate 0 dB bandwidth. We got to set it up. The gain is 5 over square root 3 squared plus omega squared. That's the gain. 0 dB means this gain is equal to 1. So again, a little bit of exercise for us to find omega. Somebody check my math. All right? Most of the time this semester, we won't be doing a calculation like this, most of the time. But we do want to understand what it means mathematically. Most of the time this semester, we're going to be generating plots and reading the plots for these numbers. And so they're going to be approximations. All right, so what we've done today is we've taken a look at frequency response. In particular, we've looked at the Bode diagram. We're going to learn this semester how to sketch them and to generate them on the computer. And then we're going to learn to read and analyze characteristics. So let's say Wednesday. Let's go back to the lab. Okay, back to the computer lab. And we'll look at some plots there.